E2 reactions, that'll be the topic of this lesson. Now, in the last lesson, we kind of had an introduction to elimination reactions, and this we're going to learn the first of two of the mechanisms that elimination occurs. We call it E2 elimination, and we'll go through that mechanism, we'll go through the rate law, and then we'll look at some characteristics of E2 reactions. We'll find out that they typically form what is known as the Zaitsev product, but we'll also learn how to predict when the exception occurs, when it forms what's known as either the anti-Zaitsev or Hofmann product instead. Now, if this is your first time joining me, my name is Chad, and welcome to Chad's Prep, where my goal is to make science both understandable and even enjoyable. Now, this is my brand new organic chemistry playlist. I'm releasing these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new lesson. So we'll start with talking about E2 reactions, and in this case we call this elimination bimolecular. So we call it bimolecular because there's going to be two reactant molecules involved in the rate determining step, just like there was in SN2. And in this case, contrast with SN2, instead of having a nucleophile and a substrate, we're going to have a base and the substrate. And again, find your leaving group and you've found your substrate. So in this case, we've got our substrate. Is our alkyl halide. And sodium hydroxide, you should definitely recall from Gen Chem as being a strong base. And just like SN2 typically involved a strong nucleophile, E2 is going to involve a strong base. And definitely sodium hydroxide qualifies here. In this case, we definitely have an ionic compound here. So what you'll find is that there are several strong bases out there, but most of the strong bases we'll see in this chapter are going to have a negative charge on oxygen. Again, there are other strong bases that exist, but most of the ones you'll talk about in the context of elimination reactions that are strong will have a negative on an oxygen. All right, way this is going to work is we're going to have sodium hydroxide come over here, and he's going to deprotonate a beta hydrogen. So that's going to free up these electrons. Hydrogen can only have one bond, so if we're making a new one here, the old one breaks, and that's where the electrons come from to make the pi bond. And so that we don't violate the octet rule, this bond to bromine has to simultaneously break. So we are doing a proton transfer here, deprotonating. We are forming a pi bond, and we have the leaving group leaving. And these all happen simultaneously. And happening simultaneously, just like in SN2, we call this a concerted mechanism. Cool, so all happens in a single step, just like SN2 typically happens in a single step. And we can take a look at our rate law here. And we see that the base is involved in this step. And we see that our substrate is involved in this step as well. And so in this case, first order with respect to the base, first order with respect to the substrate, second order overall adding those two individual reactant orders together. So if you double the concentration of the base, you'll double the rate of the reaction. If you double the concentration of the substrate, you will double the rate of the reaction as well. So the rate is proportional to each of them independently here. We take a look, and if we kind of take a look at our specific reaction, so the base is sodium hydroxide. You could just put hydroxide here. And then our substrate is 2-bromobutane here. And so there's our specific rate law for this E2 elimination. Okay, so it turns out that E2 elimination here has some stereochemical requirements we need to address as well. And I've kind of drawn it just such a way. There's actually two hydrogens on this beta carbon right here. One that's a wedge and one that's a dash. And I made sure to draw the dashed one on purpose. And so if you kind of take a look at a relationship here, so this hydrogen is pointing down and it is a dash. So in fact, let's put it right here, down and a dash, whereas the bromine is pointing up and is a wedge. And if you kind of look at where they are relative to each other, they're pointing 180 degrees apart. And it turns out they have to point 180 degrees apart. And when they do, we refer to that as being, technically it means anti-coplanar, but the word I'm going to write here is called antiperiplanar. And it turns out it doesn't have to be exactly 180. It has to just be really, really close to 180. So 180 degrees plus or minus a couple of degrees, kind of, sort of. And that's what antiperiplanar mean. It doesn't mean exactly 180, but it means really close to 180. Gives you a little leeway. So anti-coplanar is kind of the term I learned it with way back in the day. But antiperiplanar is kind of the more commonly accepted term now because it doesn't have to be exactly anti-coplanar, which again, anti-coplanar would be exactly 180 in the same plane but pointing opposite directions. But antiperiplanar means either exactly 180 or at least a little bit close. All right, so this is a stereochemical requirement of an E2 reaction. So now a lot of people don't like to draw it like this. They prefer, oh, let's rotate that around, and let's get that bromine in the plane. And that way we could get another hydrogen in the plane, and they would actually rotate all the bonds so that we could put them both in the plane. And one, I agree. I mean, that's easier to see. We can see that the bromine points this way and the beta hydrogen points this way, and obviously I haven't drawn the rest of the molecule, and it's easy to see that, yeah, they point 180 degrees opposite in their antiperiplanar. So, but you can see it here as well. So bromine here being a wedge and up, 180 degrees off, that opposite of that would be a dash and down. So cool. We can see that based on the reaction happening just as we've drawn it here, once we form that double bond, we're going to lock it into a certain conformation here. And I can see that these two methyl groups are trans to each other, and when the reaction happens, they get locked into that trans conformation. Now, on the other hand, we could actually rotate this around a little bit. So in this case, what I'm going to do is draw one more hydrogen in. So I'll draw this one in on red, and I'm going to rotate this bond around. So I'm going to move, and let's show this in green. Take advantage of all our colors here. What I'm going to do is move the methyl group to where that hydrogen is. The red hydrogen is going to go where the blue hydrogen is, and the blue one's going to go back to where the methyl is. So I'm going to rotate this single bond right here around in a circle to get the other hydrogen antiperiplanar to the bromine. You can see what that looks like. Cool, so in this case, the methyl group is now in the wedged position. So the red hydrogen is now in the dashed position, and then the blue hydrogen is now in the plane. So, and I've left that bromine right where he was. Cool, and now I can see that it's actually the red hydrogen that's antiperiplanar to the bromine. And so if the reaction happened in this conformation, I can now see that these two methyl groups wouldn't be 180 degrees apart anymore. And we can explain why we'd get the cis product forming as well. And so when you've got a beta carbon with two hydrogens attached, so assuming it's free to rotate, then you're going to get both the cis and the trans, the E and the Z, if it does have those stereoisomers, as it does in this case. Also, we could factor in that the other beta carbon over here has got three hydrogens, and at any given moment in time, one of those three is going to be in the antiperiplanar conformation. So, and in this case, this particular alkene does not have cis and trans, does not have E and Z possible. And you can kind of predict when that happens. When either side of an alkene has two identical things, there is no cis and trans. So typically you can turn cis into trans and trans into cis if you have either side and have the two groups trade places. And so if either side has two of exactly the same group, whether it be two hydrogens or two methyls or two ethyls, just two identical groups on one side of the alkene, there's no such thing as cis and trans, no such thing as E and Z. Cool. So we can see here our three products, and Mr. Zaitsev says, pick the top two. But we also know that trans is more stable than cis, and this is our major product, and these would be our minor products in this case following Mr. Zaitsev's rule. Cool, so that's the stereochemical requirement on E2 reactions. So, and this is kind of something pretty important in a couple cases, and we'll see a couple examples here where we see that importance. All right, a common type of question you'll see, really requiring you to distinguish, when this antiperiplanar hydrogen is present and when you've got to rotate a molecule to get there and stuff like that, is going to be demonstrated in this following couple examples. So in this case, we're going to predict the major product in these E2 reactions. I've got a nice strong base here. So we said our strong base is typically going to have a negative charge on oxygen. So in the last example, it was NaOH. In this case, it's going to be NaOCH3. So, and again, with metal and non-metal, that's definitely ionic. And got a negative charge on oxygen, that's a good strong base. It's essentially comparable to hydroxide. All right, so in this case, I'm going to look at our alpha carbon in both cases, and then we'll identify our beta carbons. Now, the beta carbon on the left here does not have any hydrogens whatsoever, so we cannot form a double bond here. In fact, if we tried, we'd violate the octet rule for that carbon on the left. So no options there. So, but then we've got a beta carbon on the right. And with the beta carbon on the right, there's only one hydrogen present. And so in this case, that hydrogen is on the dash. And in this case, that hydrogen is on the wedge. Cool, and that's going to be important. In the top example, that actually already is antiperiplanar to the bromine. So the hydrogen and the bromine are 180 degrees apart. Again, a wedge and up versus a dash and down, that's 180 degrees difference. So we're ready to do this elimination reaction right now. Our base would come, deprotonate that hydrogen, we'd form the alkene, kick off the leaving group, and this would get locked in the conformation in which the reaction actually happens. And in this case, that means this is going to get locked in a trans conformation, or E, I guess is more proper, as we'll see. So, but these two benzenes are going to end up trans to each other just as they're trans to each other. So in the structure of the reactant when the reaction actually happens. Cool, so it turns out this would be the E isomer. So the major functional group on the left-hand side is the benzene on this side and the benzene on this side. And when they're the two higher priority, I shouldn't say functional groups, but substituents are trans to each other, that's E. Cool, and we don't observe the Z product in this reaction at all, so only the E. And the idea is that when your beta carbon only has one hydrogen, if E and Z exist for that compound, you're only going to get one of the two because that hydrogen is only going to be antiperiplanar in one of the possible conformations, leading to only one of those products. So if we look at this next one here, there's a couple different ways to approach this, but this wedged hydrogen is not 180 degrees away from the bromine right now. It's just not. And so we're going to have to rotate this around before the reaction can actually happen. And so just like we did on the last example here, what we're going to do is we're going to move this hydrogen to where the methyl group is. We'll move the methyl group to where the benzene is, and we'll move the benzene to where the hydrogen is. We're going to rotate this bond right here between alpha and beta, in this case, 120 degrees. So until the hydrogen is antiperiplanar to that bromine right there. So let's rotate this around. All right, so in this case, the benzene is now in that wedged position. So our hydrogen now is in the antiperiplanar position to the bromine. So, and then finally this methyl group is now in the plane over here. And now this reaction's ready to go. And we can see that it's not the two benzenes that are going to be trans to each other, it's the benzene and a methyl group that are going to be trans to each other. And so our base again is going to come and deprotonate the antiperiplanar hydrogen, which frees up those electrons to form the alkene, causing also the leaving group to simultaneously leave. And so if we draw our product out now, so we see that we actually get the Z product. Now the two higher priority groups are on the same side, we say. So they're cis to each other. And so we get the Z product. Cool, and we only get the Z. We're not going to get the E in this case at all. So cool, we had to do some rotation and stuff like this here, but there is a little bit of a cheat here. What we could have done is said, if the reaction happens right now in this conformation, well then we get the E, just like we did above, right? So is it ready to happen? Well, it's not, because the hydrogen's not antiperiplanar. So then you're not going to get the E conformation. You'll get the Z instead. So I took the time to rotate the bond and show us, show the hydrogen and the bromine in the antiperiplanar conformation. But the truth is, if the reaction is ready to happen, great, like the one above. So where the H and the B are antiperiplanar, great. Then you know what the conformation is going to look like. So in this case, though, if the reaction is not going to happen, then you don't get the E. You get the opposite, in this case, the Z. If it happened in this conformation, we'd get E. Since it's not ready to happen, we'll get Z instead. So just a little trick, little shortcut. But again, big key here is if you only have one beta hydrogen, then if E and Z are possible, you only get one of the two, depending on the arrangement you've got. All right, in the next example here, we definitely want to cover cyclohexane because there's something special with cyclohexanes when it comes to antiperiplanar hydrogens and stuff. So first of all, using a strong base here, so we'll know we're doing an E2 reaction. We'll find out that E1s use weak bases just like SN1 use weak nucleophiles. So in this case, got a negative charge on oxygen. In this case, it's sodium ethoxide, sometimes written as NaOET, but a nice, good, strong base that we commonly see when dealing with elimination reactions. So, and if we look here, our bromine here is on the alpha carbon, and in this case, we have got two beta carbons. And if we draw in their relevant hydrogens here, we got one here, and over on this one, we've got two hydrogens, one a wedge and one a dash. And that's going to be important. Now, most single bonds are free to rotate, except when they're part of a ring. So a single bond that's part of a ring here, any one of these single bonds that's part of the ring, might have a little bit of rotation as possible, like when we're switching chair conformation stuff, but it just can't rotate freely like a single bond that's not part of a ring can. And that's important because if a hydrogen is not antiperiplanar, then it's never going to be. So, and that's important. And ultimately what that's going to mean here, and I'll just kind of give it away, is the hydrogen that's going to be antiperiplanar has to be trans to the leaving group. So if I look at bromine being on a wedge, to be trans, my beta hydrogen has to be a dash. That one's not going to work. That one's not going to work, but that one will. So out of our 3 beta hydrogens, only one of them is even possible. It's only one of them is possible to react in an E2 elimination reaction. So cool, Mr. Zaitsev would have said, hey, look down here. This beta carbon only has 1 hydrogen. This one has 2. Use the beta carbon with fewer hydrogens, i.e. use the more substituted beta carbon. So, but we're not going to follow Mr. Hofmann's rule here. So when it comes to E2 reactions, this idea of having antiperiplanar hydrogen takes precedence. And this is one example where we'll find out that we'll do Hofmann elimination instead of Zaitsev elimination. All right, one thing we should do to kind of map this out is draw the chair conformation. Cool, and what I'm going to do, so bromine is a wedge, so I'm going to point that bromine straight up. So, and as we come over here, the methyl group is going to be straight down, and that hydrogen there is going to be equatorial over here. So, and then on the adjacent carbon, we've got a hydrogen pointing straight down, and then an equatorial one slanted off over here. And you can see that it's this hydrogen right here that'll kind of circle in red. That one points 180 degrees away from the bromine here. And so in this case, that's our antiperiplanar hydrogen. That's the one involved in the reaction. We can see that this hydrogen over here on the more substituted beta carbon, it's not antiperiplanar. If bromine points straight up, I needed it to point straight down where the methyl group was, but it doesn't point there. So that's why this hydrogen over here, it's not possible for it to react in this particular reaction. One other thing you should note is that when you've got a chair conformation, you typically have 2 chairs in equilibrium. So, and it turns out only when the leaving group is axial, and we'll find out that it and the hydrogen that's antiperiplanar will be trans-diaxial, but only when the leaving group's axial is this reaction even possible. So in this case, we arrange this bromine is now going to be over here and be equatorial. So, and on the adjacent carbon, let's get that methyl in first. And draw in the relevant hydrogens. So, and here's that trans hydrogen here, but when they're equatorial, they don't point 180 degrees apart, and the reaction can't happen. And so we've got this equilibrium going. We need this conformation with the leaving group axial for the reaction to actually happen. Anything that hinders the formation of this particular chair conformation would slow this reaction down. So if I put a t-butyl group somewhere that forces it all to be in this conformation or mostly all in this conformation, you can actually shut down an E2 reaction completely. So, but the key is only one of the 2 chairs is actually going to be usable in an E2 elimination reaction here. All right, so if we go back to our product then in this E2 elimination, so we'll form the double bond right there. So, and once again, we'll call this the Hofmann product. Or some people say anti-Zaitsev. Take your pick, but Hofmann's a little more, oh, and I can't spell apparently today either. So, because that is not how you spell Hofmann's name. It is a little bit of funky spelling though. 1 F, 2 N's at the end. So, and that's your Hofmann product. In this case, the Zaitsev product wasn't even possible. All right, so we've already seen one example where we might not actually preferentially follow Mr. Zaitsev's rule and do Hofmann elimination. So, and here I want to show the most common example of where you're actually going to do Hofmann elimination to get the major product. And it involves what we call a bulky base. So, and you can kind of see why they call this a bulky base. This is here potassium t-butoxide, and sodium or potassium t-butoxide is the most common bulky base. In fact, for many students, it's the only one they're ever presented with. So if we look at it here, the oxygen here, and again, this is ionic. So potassium's got a positive charge being a metal, oxygen being a non-metal's got a negative charge. And in this case, the negatively charged oxygen is bonded to a tertiary carbon. So, and that gives it some bulkiness associated with it. And as a result, it turns out it looks over at our beta carbons over here. We've got, in this case, our alpha carbons where the halogen again is bonded, and it's a tertiary carbon, which means there are 3 beta carbons, 2 that are secondary, and 1 that is primary. So let's give myself a little room here. And if we look here, the secondary ones each have 2 hydrogens, but the primary one out here have 3 hydrogens. And the idea is that our bulky base is like looking over here and saying, well, I got to deprotonate one of these beta carbons, but man, I'm big. And I'm just so big, you know, I just think I want to not get too close here because, you know, that would be a little uncomfortable. Let me just deprotonate the primary carbon. Cool, instead of the secondaries. And so it turns out he's, just due to his bulkiness, his sheer size, that's what he prefers to do typically. And as a result, we don't get the product we expect as the major product. We're going to disobey Zaitsev's rule here and form the double bond using the primary beta carbon. So rather than following Zaitsev's rule and using either one of these secondaries, and it turns out due to symmetry, they're equivalent. So whether you form the alkene here or here, it's exactly the same thing. So we call the one on the left the Hofmann product, or the anti-Zaitsev product. And in this case, that's going to be the major product now. We'll call the one on the right still the Zaitsev product. But this time around, it's going to be the minor product. Now, sometimes, you know, somewhere down the line, we'll present you with something. We'll talk about the most stable product being the thermodynamic product. So, but in certain cases, you can actually have what's called the kinetic product be the major product, like we're doing here. So this is one example of that. We'll definitely teach you some further down the road when that's the case. But this is the kinetic product here, this Hofmann product. That's going to be the major when we use this bulky base. Now, it turns out that not every time you use a bulky base do you get the Hofmann product as the major product. But it's a little confusing to teach you when exactly you do and when you don't. So most of the time, most textbooks and most professors just kind of oversimplify this and they just say, anytime you use a bulky base, you're going to get the Hofmann product as the major product. So, well, in this case, the truth is this. So for those of you that might have been presented with the truth, if you use a tertiary halide, which I'll call a bulky halide, then yes, you're going to get the Hofmann product as the major product. But if you use a secondary halide, well, some secondaries that are bulkier still form the Hofmann as the major. But some secondary halides that are less bulky form the Zaitsev as the major, and it gets a little confusing, which is why for most of you, you're just going to be simply told to memorize that when you use a bulky base, the Hofmann product is the major product. The least substitute alkene is the major product. All right, I want to present to you one more example of where you might actually get the Hofmann product. Instead of the Zaitsev as the major product here. So in that case, it turns out when you have a bad leaving group, in fact, Hofmann actually got his name on the Hofmann Elimination, which is properly a reaction of amines, for specifically a reaction involving a bad leaving group. Now, this wasn't the bad leaving group he dealt with, but it's the one we're going to deal with here in this chapter, the most common one presented. Now, for many of you, you may never actually see fluorine as a leaving group. But if you do, fluorine is not a good leaving group. It is not a weak base like chloride, bromide, and iodide, or not a super, super weak base anyways. And being a little bit stronger base, he's not a good leaving group. And when you don't have a good leaving group, you often get the Hofmann product as the major product here as well. And so in this case, I still got a good strong base, and he's not a bulky base this time. We don't need the bulky base here. We just need a bad leaving group. That's another way to get the Hofmann as the preferred product. And in this case, once again, our major product is the less substitute alkene. And once again, this is a kinetic product. So it turns out, if we kind of take a look at what's going on here, that's not an O. Let's make it an H. So we're going to come and deprotonate that beta hydrogen. And that frees up these electrons to form the pi bond. And so we're like, okay, let's form that pi bond so that fluorine can leave. And fluorine's like, whoa, 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 slow down, guys. I suck at leaving. Let's just take this a little slower and let's back things up. So let's undo this. And yeah, hold up on those electrons. And this carbon's like, dude, hydrogen's gone already. You need to leave. And so we kind of get a little buildup of charge on that carbon. Now, this is not the proper mechanism. The proper mechanism, this still all happens in a concerted fashion. But it turns out in the transition state along the way, there is a buildup of charge on that carbon, and it is on the beta carbon specifically, and it's very anion-like. So we have a little bit of a carbanion-like transition state, and I'd rather have a carbanion on a less substituted carbon. So for carbocations, they're more stable with more substituted carbons, but carbanions are more stable with less substituted carbons, and that's why we chose to have this carbanion-like transition state on a primary carbon instead of on these secondary carbons. So we're still not forming the most stable product. This is still a kinetic product. But due to having a bad leaving group, little buildup of negative charge on that beta carbon. Again, if you're going to properly show the mechanism, though, it's still all a concerted mechanism. It still all happens in one step. But we just know that in the transition state, there is that buildup of negative charge on the beta carbon. Now, if you found this lesson helpful, consider giving me a like and a share, a couple of the best things you can do to support the channel. And if you've got questions, feel free to leave them in the comments section below. Now, if you're looking for the study guide that goes with this lesson, or if you're looking for practice problems, I've got practice quizzes, chapter tests, practice final exams, all part of my premium course on chadsprep.com.